For our final project for game physics, we proposed a sand surfing game featuring a character sliding down a hill, based on the video game Journey. Here's a short video of the original game. So our main idea was to create a 3D environment consisting of a slope, the area of which will act like sand based on the dunes in the original game. The main character will be pulled downward by gravity and slide down the hill. The user will be able to control the main character. As an additional challenge, we wanted to add cloth physics to simulate the movement of the scarf and cape of the character like in the original game. Originally, we wanted to create our project in Unity 3D, since it already has a lot of functionality built in. Things like 3D collision detection are hard to implement from scratch, so it would save a lot of time. However, we weren't satisfied with the way the result looked in Unity, and while Unity has a lot of functionality already built in, this also brought a lot of restrictions with it. So that's why we decided to build the project from scratch in C++ and OpenGL, and we moved everything we had already built in Unity to there. The surfing behavior of the player is implemented in the standard rigid body dynamics way. The player is affected by the force of gravity, and when it comes in contact with the terrain, an impulse is applied in the direction of the normal vector of the contact point. The velocity of the player is then computed based on the external forces and impulses acting on it, and the new player position is determined by integration. For integration of the player position and velocity, we use the semi-implicit Euler method. We chose this method because it is more accurate than explicit Euler, but just as fast, making it perfect for real-time games. To prevent the player from falling through the terrain, we cast a ray downwards. The origin of the ray is slightly above the player position so that a potential collision is not missed. If a collision is found, then the player position is corrected to the entry point of the ray with the terrain to solve the interpenetration. For every update, we also take user input so the user can move the player object. The keyboard is used to rotate the player and to provide forward and backward motion in the direction the player is facing. When the user moves their mouse to the left or the right side of the screen, we rotate the camera around the player. The camera is always a certain distance away from the player and keeps them in focus by using a look at view matrix. Since it is also possible for the camera to dip under the terrain, we also cast a ray from the camera to the terrain in order to permanently keep it above the ground.
In addition to the rigid body dynamics of the player, we also implemented cloth physics for the cape and scarf of our player object. We performed this cloth simulation using position-based dynamics. This is a fast simulation technique that models various constraints between vertices of a model. These constraints define how the vertices interact with each other and with the world. For example, for a cloth simulation, we add distance constraints to all the edges of the cloth model. This is so that the vertices try to stay the same distance from each other. We would like to model the clothes of the player as a non-elastic fabric. This means that the length of the edges in the cloth doesn't change during the simulation. To accomplish this, we define distance constraints on all the edges during initialization of the game. These distance constraints make sure that the cloth keeps the original length of all the edges in the model the same. In a position-based dynamic simulation, these constraints are modeled as equality constraints. This means that when the length of a constrained edge is equal to the length prescribed by the constraint, then the constraint is satisfied. If it's not the case, then the dynamic solver will need to move the vertices of the edge in such a way that the constraint does become satisfied. At every time step, the position-based dynamic solver attempts to satisfy all the constraints defined in the system. This is done in a kind of Gauss-Seidel kind of manner where it attempts to solve each of the constraints sequentially. It resolves them by projecting the vertex positions to new positions such that the current constraint is closer to being satisfied. If a constraint has already been satisfied, then we don't have to update the proposed positions and we mark it as resolved. If after dealing with all the constraints not all of them are satisfied, then another pass needs to be done over all the constraints. This process continues until either all the constraints are satisfied or until a user-defined maximum number of iterations has been reached. In our program, we have found a maximum number of 10 iterations to provide accurate results at low computation cost. We need to make sure that the scarf and cape will remain attached to the player object and won't be moved by any constraints. In order to do this, we manually marked some of the vertices on the mesh as fixed. If a vertex is marked as fixed, we do not compute the new positions by integration, but instead update the position of the vertex directly using the current position of the player object to ensure it always moves together with the player. In addition to distance constraints, the clothes of the player need to collide with the player itself, otherwise they would just fly through him. To address this issue, we implemented collision constraints. These are inequality constraints that attempt to push a given vertex out of the colliding object if it tries to get in, or is already inside. In order to generate these constraints, we cast rays from all cloth vertices. Should a ray intersect the collider, then a collision constraint is added to that vertex. The position-based dynamics paper describes two ways of collision detection. Continuous collision detection attempts to stop a moving vertex from entering another object. This is done by continuously casting rays from the vertex position of the last frame to the proposed vertex position. If this ray hits an object on the way, then the proposed position is invalid and an inequality constraint is generated that must be satisfied. The problem with this kind of detection is that the differences in vertex position between two frames might be very subtle. This means we cast an extremely short ray that's very likely to miss the collision event. We found that for the sometimes gentle movements of the cape and scarf, this resulted in poor collision detection. If the continuous collision detection has indeed failed, that means that there's a vertex inside of the player body, for example. And then we have to resort to static collision detection. Here we simply find the nearest surface point to our vertex and define another inequality constraint to push that vertex out of the body. This detection resulted in a lot more stable interaction between the cloth and the collider, in our case the player body. And now we would like to show you a short video of our finished project.